It's a lonely morning. I guess there's no food right now, so that that's what does it.
Oh, is this not on? Oh, okay. Mark mentioned that it would turn on. Yeah.
If you tap it,
Tap.
the microphone part.
Good?
Is that good?
Yeah. Okay, it's good. I got a thumbs up. Wondered what
I'll wait like 2 minutes.
Sure. I'm gonna roast Morgan if he doesn't show up.
That would be pretty.
I know.
Also
And Lika
floor.
and Floor.
Yeah.
Absolutely, we'll have a tweet.
You just tweet at that
Mid-talk. Yeah.
Where are you?
That's funny. That's okay. Also, I would have guessed I could have pulled Warren out. Warren Brown.
Yeah, I think he also, did he sign up to meet with you?
Yeah. So maybe that's the.
He's like, eh.
He's like, yeah, I'll hear about it.
Yeah.
I've heard enough of your stories.
It's only 11:01.
Yeah. Oh, right. Okay, that clock. Now I get it.
Yeah.
That clock is like deceiving.
Yeah.
Maybe. Okay. No. What am I doing? I moved it, and that was a bad call. Let's try this again. Sorry. Good thing it's only 11:02. What did I do?
I'm just thinking, I'm just
Did I
here.
bust it?
Look at it. Hope that
I
helps.
know, that's what you do, right? There we go. Sure. Good. You had to stand up and really give it the business.
I'm very threatening,
Yeah.
especially to computers.
Okay, so let's start. Good morning, everyone. We're excited to hear today from Katie Breivik, who's coming to visit us from the CCA. Before she was at CCA, Katie was at CETA, and before that, she was a grad student at Northwestern. And in the fall, she's moving to start an assistant professor job at Carnegie Mellon. Katie's well known for lots of work on binary evolution, making predictions for LISA, interpreting gravitational wave sources, and also good practices in open software. So we're excited to hear from her. Go ahead.
Cool. Thanks, Kareem. Thanks for that lovely introduction. Super stoked today to get everyone in this room as stoked as I am about LISA. If you don't know what LISA is, how it works, hopefully by the end of this talk you will understand at least that, and enough to like really tell people that like, yes, you should continue to fund LISA science because it's going to be great. Good. Okay, so I like to start every talk with some drama. I posit that if you currently do not care about binary stars in your science, you will in the next few years, like for sure. Binary stars are a critical component of basically all astrophysics, or they're a limiting noise source for you. So either way, my understanding and excitement about binary stars benefits everyone in this room. So you should be stoked about them. And it's really absolutely the case. Like it really is the case that binary stars drive galaxy evolution. They are the largest noise source for exoplanet populations. They're actually also the largest noise source for finding clumpy dark matter in stellar streams. They are super annoying for people who do resolve stellar populations because you don't always take binaries into account. And of course, multi-messenger astrophysics, they really are the name of the game here. They are the sources of all gravitational waves, basically. So that's not cosmological stuff, but the majority of gravitational waves are really coming from binary stars. That's because most stars have a companion. Like we point our telescopes, you look out, if you have a survey that can tell if there's a binary companion, most of the time, when you observe a star and look for a companion, you're going to find one. It might be at a close orbital separation or a wide orbital separation, but the higher in mass you go, the more likely this becomes. And that's very interesting from a physics perspective, because a binary companion introduces the potential for really, really interesting interactions. And these are like really physically just like interesting systems to study. And so that's what I spend most of my time thinking about, is what happens when two stars interact. And I really don't discriminate against mass or separation or anything like that. I'm excited about all kinds of stellar interactions. To give you a flavor of what kinds of interactions I'm talking about, I like to go through a very cartoony version of binary star evolution, and this also gives you a flavor of the kind of science that I do. I don't actually run stellar evolution codes in real time because that is impossible to do for large binary populations. Instead, we try to think fairly qualitatively and holistically about all of the evolution and apply as much quantitative physics as we can along the way. So say you start out as a binary star, and in this case, you're going to be the timescales here are for massive stars. Fairly quickly, the more massive star is going to exhaust the hydrogen in its core. It's going to evolve off the main sequence. As it evolves off the main sequence, it gets large, and if it's in a binary, it's going to fill its Roche lobe. One thing that it can do, if it fills its Roche lobe, is go into a stable mass transfer phase where it donates its envelope to its companion. And that companion maybe can accrete most of the material, maybe it doesn't accrete a lot of the material, but we have models that tell you how the orbit changes depending on how that process works. Soon after, it will leave behind a stellar core, naked helium star. These are often thought to be maybe their Wolf-Rayet stars, but what it is a star after its envelope has been stripped. Fairly quickly after that, that stripped star will form a compact object like a black hole. This process is very uncertain. We don't actually know exactly how stars turn into compact objects, and we also don't know what that does to the orbit, but we have prescriptions for all the things that can happen. If a black hole forms in a neutron star, forms in a supernova explosion, we have models to say how the strength of that supernova explosion can alter the orbit. If it instead collapses directly, we can also just say the black hole collapses directly and there's no supernova explosion. Good. Okay, so now you're left with a bright star compact object companion. Eventually, that initially lower mass star will also evolve off of the main sequence, and it can potentially fill its Roche lobe, go into a stable mass transfer phase. This is a very common X-ray binary type system that we know of in our galaxy. That will again leave behind a stripped star with a compact object companion. That will make a double compact object eventually here. Maybe there's a supernova, a kick again, we don't know. And then once this happens, all that you have to do is emit gravitational waves over very long timescales that will shrink and circularize your orbit, eventually creating a merger that's observable by ground-based detectors. This is one track that you can do. If instead the mass transfer of this initially less massive star does not remain stable, you can go into something that we call a common envelope evolution. This is a wildly uncertain phase of stellar evolution, but is something that we have invoked because we have observations of close double stellar remnant pairs that absolutely would not fit inside of the orbit by any other mechanism than to have a very dramatic orbital shrinking. So of course, we have prescriptions that tell you how this could work based on things like orbital angular momentum conservation or orbital energy conservation, but it's very uncertain. Good. Okay, so that will leave behind, again, a usually closer system and is much, much faster on the timescales. So this stable Roche overflow tends to happen on thermal timescales, while common envelope happens on dynamical timescales. So that's like, it's really fast. We're basically only going to observe a real common envelope evolution as a transient type system. And indeed, luminous red novae have been suggested as maybe they're common envelopes, but we haven't confirmed that yet. Good. Okay, so again, you'll make double compact object and a merger. One thing that's very different about these channels is the delay time to make those mergers. Because stable mass transfer results in overall wider systems, they're going to have longer delay times. So that's an observable that we can use as a lever arm. Good. Okay, so this is one arm. Of course, you can kind of see in the forecast what's coming for the bottom half. What's coming from the bottom half is instead, you could go into a common envelope with the primary star, or the more massive star, going unstable, creating a strip star, compact object with a bright star. Same story here, same story here. This encompasses basically everything that I think about on the daily basis, but I don't only think about black holes. So you can basically tell the same story for white dwarf progenitors as well as neutron star progenitors. And the thing that changes the most is the timescales to the formation. White dwarfs take a long time to form relative to their more massive stellar counterparts. And the interaction scales are actually much tighter as well. So white dwarfs can interact on AU scales. Black hole progenitors can become enormous and interact on much wider orbital scales. Cool. What I want you to take away from this in words is, first, Roche overflow mass transfer is the dominant uncertainty in binary star evolution. What happens when a star fills its Roche lobe determines the rest of the orbital evolution from that point on. And so understanding the outcomes of Roche overflow helps us understand how binary star populations shape the galaxies that they exist in, but it also tells us what double compact objects we're going to get out and what the characteristics of that population looks like. To a lesser degree, but a very important degree, compact object formation really plays a critical role in the characteristics and rates of double neutron star and double black hole populations. And the reason for that is because if the dominant formation for compact objects is a giant supernova explosion, 90% of the time that's going to unbind your binary, and that takes away a lot of the double compact object sources that we could observe. Good. Okay, so I personally do something called binary population synthesis that provides a means to understand how these uncertain physical processes propagate through stellar populations. So we have prescriptions for all of the kinds of binary interactions you can imagine: tides, magnetic braking, Roche overflow, neutron star kicks, winds. We tune all of those parameters and then see how different tunings map their way through to observable populations. I spent my PhD basically creating a code that is openly developed and easy for people to use and install to simulate any kind of binary population that you want to. It's been used to do a lot of kinds of science, which has really been probably the most fulfilling thing of like doing open software. People come up with really fun ideas. So in particular, the latest thing that we did that I really was like, I don't know if we should do this. We used Cosmic to study tides and planets, and it worked like really well. So you can use Cosmic to do X-ray binaries, double white dwarfs. We've coupled it to a globular cluster code called CMC, so it's running there so that we can make direct apples-to-apples comparisons of dynamically formed systems versus isolated systems. Today's talk is really focused on LISA, but if you're interested in any of these kinds of things, I'm very excited to chat with whoever about really anything binary stars, survey selections, or open software. Cool. Okay, so that is the first, that's like the prelude of the talk. Now we're going to talk about LISA, and we can be dramatic here too. LISA will absolutely transform stellar evolution. Like, no question, will transform stellar evolution and stellar remnant science because it is complementary in very awesome ways to both ground-based detectors as well as electromagnetic surveys. So the roadmap for the rest of this talk is to basically get everyone up to speed on what's happening with LISA, how does it work. Then we'll talk about what it will do for neutron star and black hole binaries. And then we'll talk about what it can do with white dwarf binaries. This is by no means a deep, single result type of talk. This is a very broad talk. That means if I don't cite your favorite person's thing, it's not because I don't care about it, it's because I'm like flying through science as fast as I can because there's so much that LISA can do. All right, so first thing that everyone always asks is what's happening with LISA and when does it launch? Right now, the date is 2035. that sounds long for a lot of people. That's like nothing for gravitational wave detectors. And this is a $1 billion class mission. The reason that the 2030s really doesn't sound long at all is because the second that you start turning wrenches to build this system, it's going to take you at least 8 years. So until we start turning wrenches on LISA, we have an 8-year lead time. We're about 2 years away from doing that. We'll finalize the mission structure, which is like observation duration, how much propellant we're going to put on it, exactly what types of little doodads are going on, the detectors that are going to house test masses that we shoot lasers between. That finalizes like by the end of next year. So LISA is happening. It's real. There's a lot of money that's already been devoted to it. So folks who are not, don't want to work on something that's going to just get canceled, which is a fair thing, we're not in that phase anymore. We passed that in 2015. And the reason for that is because we flew a Pathfinder mission that showed that you absolutely can launch LISA and it will work the way that you want it to. And ground-based detectors showed there are a lot of gravitational wave sources out there and you guys are idiots if you don't launch this thing. And I'll explain more about why that is in just a second. So LISA is very different from ground-based detectors and it has to be launched into space because the size of the detector is enormous. It's 2.5 million kilometer long arms. Those 2.5 million kilometer long arms make it sensitive to orbital periods of roughly 90 minutes to 20 seconds. Conversely, ground-based detectors are sensitive to kilohertz frequencies, so like 1 millisecond. So that's why very, very different gravitational wave sources. If you're not used to thinking about gravitational waves, instead of thinking about photometric limits, radial velocity limits, we think about these things called sensitivity curves. So this on the x-axis is the frequency of the gravitational wave. For circular orbits, that's just 2 times your orbital period. So that's nice. It's really lovely because it gives you a direct dynamical measure of that binary that you're looking at. People who search for orbital periods and binaries with telescopes know that's a huge pain to try to get really nailed down, and you have to do a lot of work. For gravitational waves, it basically comes for free. On the y-axis is something called the amplitude spectral density. This is basically the square root of a power spectrum of gravitational waves that are emitted. And then because the sources in the LISA band don't evolve very quickly, you just build up power over time. And so that amplitude spectral density takes into account how much power you build up in an observation. So this is the LISA sensitivity curve. There's a little bump here. That bump is actually an astrophysical noise floor that we put in. I'll talk about that more in a minute. The shape of this curve is actually pretty qualitatively easy to describe. At the low frequency end, this upward slope literally is the limit on how well we can measure the position of the test masses over long periods of time. The longer the time you observe something, measuring the position of the test masses to an immense precision gets harder and harder and harder, so your sensitivity degrades at low frequencies. This is the noise floor for how well you can isolate the test masses. So that's just keeping them not bogged down by little jolts and jiggles. The largest noise floor here is actually the solar wind pressure, which is interesting. So this will be placed kind of like a nice limit on solar radiation pressure. I don't know if that's a valuable thing for solar physicists, but it'll be a limit nonetheless. And then up here, this is actually, at higher frequencies, the sensitivity degrades because the physical size of the gravitational waves gets smaller than the size of the detector, and so you get some interference in there. And you see a really cool beating pattern that happens here because these are literally the harmonics of the size of the detector. So for LISA, a source is detectable if it falls above this curve, and its signal-to-noise ratio is literally, in the amplitude spectral density space, the height above the curve that it sits. Cool. LISA is going to observe so many kinds of sources. When people think about gravitational waves today, they think about merging double compact objects. That's the primary source for ground-based detectors. And that's what's happening in the kilohertz regime. There's a few other sources that we should be able to observe, like supernovae and continuous wave sources with ground-based detectors, but that's third generation. The millihertz band is stacked. We have merging supermassive black holes. They're going to come in here with signal-to-noise ratios potentially of 10 to 20,000. That's ridiculous because you can actually measure the distance and localization of merging supermassive black holes basically out to redshift whenever they form. And as these black holes come in and merge, we get better and better localization that we tell to our friends who use telescopes. They measure the redshift, and you have an independent Hubble constant measurement out to something like redshift of 7 or 8, which is just completely not doable any other way. That turns out to be actually the flagship reason that we're flying LISA. I'm about to tell you about sources that are kind of like the trash of LISA, but there's still a lot of science to do. There's also these really fantastic sources called EMRIs, which are extreme mass ratio in spirals. The extreme mass ratio comes in because you have stellar mass objects orbiting and falling into supermassive black holes. As they do this, they trace out the space-time of the supermassive black holes, and they actually emit gravitational waves at all these different harmonics, because as they orbit, they zoom in, and then they orbit really fast, and then they zoom back out, and they do these really, really wild orbits that literally trace the space-time and will provide the most stringent test of GR that we have predicted so far. Here, these are some, I'll talk more about these a little bit later. These are actually systems that we put on the LISA curve after LIGO detected GW 150914. That's because we realized, oh my God, there will be binary black holes that LISA can observe, and they will chirp into LIGO, which is very cool. The largest source by number are just the double stellar remnants laying around in the Milky Way. And that's what the rest of this talk is going to focus on. Close double stellar remnants are really fantastic gravitational wave sources because there are many of them, and they are very easy to describe. Their gravitational wave strength depends on this funny combination of masses called the chirp mass, their orbital period, and their distance. And you can basically write this down for any close binaries that we know of. We know of quite a few close binaries because amazing observers have been looking for close binary double white dwarfs from something like 10 to the 5 candidates. Right now we know about most of them from work actually led here, the ELM survey. The ELM survey has thrown down something like 100 double white dwarfs with very low masses. And they basically found them through a color selection, which is really, really clever. And then did RV follow-up and confirmed, yes, basically everything that's an ELM is a double white dwarf. Why is that? That's because masses less than 0.3 solar masses should not have made a white dwarf by today. That process takes 15 gigayears. And so if you color select on white dwarfs that are 0.3 solar masses, you're basically guaranteeing that you find a binary. That was the idea. They knocked it out of the park. They basically have consistent with 100% binary fraction of ELM white dwarfs. So that's a good way to find them. Unfortunately, they're biased. These are all the lowest mass white dwarfs. So it's not really indicative of the entire sample, but nonetheless, it's a fantastic sample. There have also just been radial velocity surveys of known white dwarfs. The swarms and SPY teams have done this, and you can see they have a harder time picking them out because if you just pick a random white dwarf, you have to take a spectrum, you have to get a lot of very high resolution spectra to measure radial velocity shifts. That's a hard thing to sell in TAC land. Because no one wants to look at 1,000 white dwarfs with like Keck. Like you really have to have an inroad to convince somebody to do that. And so this is what we get. And then of course, more recently, ZTF, who is looking at mostly photometric variation, so searching for eclipsing white dwarfs, has started to churn these things out like crazy. It's not by chance that this is happening. Tom Prince basically wrestled the ZTF people at Caltech into looking at the galactic plane. Most transient surveys for a long time have been like, whoa, there's so many stars here. Like, let's do 20 degrees and just like never look at where the stars are. And then they say, hey, you guys, there's no double white dwarfs. Like, where are all the double white dwarfs? And the answer is they're in the plane, and you just have to look for them. But it's super, super hard. So finding double white dwarfs photometrically is like one of the most valiant, thankless causes in astronomy because it is very hard. But it will be valuable in the future. Because of the work of these surveys and easy theory that I will advertise here, this code that you can use to calculate LISA SNRs, genuinely, if you have close double white dwarfs or close binaries at all, if you know of a binary that's less than an hour, download this code and see if it's detectable by LISA. It'll be 2 lines. We need to find more sources that are detectable by LISA. Good. Because of those surveys, we actually know of like something like 30 sources that just are out in the galaxy. We know exactly where they are. We know exactly what their orbital periods are. And we know that they're going to be super loud sources for LISA. So this is one of the things that I'm very excited about, and I'll talk more about why that is. These known sources are biased in many, many ways. They're either the lowest mass white dwarfs or they're the closest systems. That's not enough to convince people to fly LISA for galactic binaries. So the rest of our motivation comes from theory. And I'm going to just very quickly go through like crayon level reasoning for this. So first, white dwarfs make up 99%. Fine, that's an IMF, that's easy. Population synthesis, lots of us here, have predicted and said, okay, pick your binary evolution model, take an IMF, just forward model the fact that we know that most of the stars are white dwarfs, many stars are in binaries. We expect there to be tens of millions of double white dwarfs in the galaxy, so surely there's tons of them for LISA to observe. If you're not stoked about white dwarfs, good news. The rest of the stellar remnants are neutron stars and black holes, and those can also be in binaries too, that LISA might observe. And again, people have predicted what we expect LISA to see here. And there are something like tens to hundreds, depending on your binary evolution uncertainties, for LISA to observe. So we have tens of millions of sources in the galaxy. How is LISA possibly going to measure these things? I like to think about LISA as like a frequency board here. It's kind of like Plinko, if people watched like The Price is Right. But you basically have all of your binaries out in the galaxy. They have an orbital period, which you can convert into a gravitational wave frequency here. And depending on their frequency, they end up in a bin. The widest binaries go into the lowest frequencies. And then you can just basically do this. LISA will do this. It'll watch for 4 years and put all these binaries in bins. Good. So yeah, so LISA, no, never mind. I'm going to say this in a second. By virtue of astrophysics, we know that these sources, actually not astrophysics, GR, by virtue of GR, we know that, and astrophysics actually, most of the sources are just evolving due to gravitational radiation emission. So we know that their orbital evolution is just this equation. That equation tells us that systems with low frequencies evolve much slower than systems at high frequencies. That means that you get 2 million more systems here than you do here. So you got a real big pileup at low frequencies to deal with. That's just from astrophysics. It's not LISA. Where LISA comes in is it has a frequency bin sensitivity. So the width of these bins is actually something like 10 to the minus 8 hertz. And so LISA does 1 second time sampling. So you can literally just say, OK, the frequency resolution is 1 divided by that observation time. And so what that means is there are 10,000 bins, 100,000, a million, 10 million bins to put your binaries in. That combined with the fact that we have this massive pileup means that there is a lot of confusion going on here because there's a lot of gravitational waves being radiated over the top of one another. When you actually do a simulation, count up all of the double white dwarfs that you expect in the galaxy, give them a position, calculate their gravitational wave strain. This is what it looks like on the amplitude spectral density. So every line here is basically either overlapping signals of double white dwarfs or an individual double white dwarf if it's in its own bin. We've divided up the frequency by just literally taking a Fourier transform of the data. There are some interesting features here. One of them is an artificial feature. So right here at about 10 millihertz, double white dwarfs can also fill their Roche lobes. What happens when that happens? We don't know. We don't know exactly what happens when double white dwarfs fill their Roche lobes. You have to treat it very carefully. We've done things like three-body dynamics where you actually just ballistically take mass off of a white dwarf, see how it changes the orbital angular momentum when it gets accreted. You can do that, but if you're doing these giant population simulations, that's a headache. So a lot of people just say, chuck them. Cut it off. We're just going to take detached double white dwarfs. There's good reason for this, because if the double white dwarfs go into unstable mass transfer, they're going to merge. That's not a LISA source, so fine. If they stably mass transfer, their mass ratios are going to get really lopsided, and that actually gives them, they come in due to gravitational waves, transfer mass, and then they actually period bounce out, so they go to lower frequencies and have lower signals. So they're almost certainly buried in the noise anyways. So doing this artificial cut isn't the worst thing for doing population statistics. Cool. Another feature is right about here, right about 1 millihertz. We say that binaries with gravitational wave frequencies below 1 millihertz are very likely to be unresolved. And what that means is that they are just overlapping signals with another white dwarf somewhere at that frequency. A really obvious feature of this is actually this noise floor here. That is an astrophysical noise source in the millihertz regime that you will not get below unless you subtract it out. So the largest noise source for LISA is actually a signal, which is cool. As I said before, there are something like 10 to the 4 binaries above and 10 million binaries below. So in terms of thinking about what LISA looks like, the big question is, are you making binaries that are in this regime that will be individually resolved as sources? Or are they going to be in this regime where it's just a gravitational wave power spectrum? There's physics that you can do with both. I don't have a ton of time to go into this physics, but we'll talk a lot about these resolved binaries. Yeah?
The really false light on the left side, is that a black hole, or why do you get ones that are?
That is an anomalously close white dwarf to us. So it's just very nearby. So what changes your height on this amplitude spectral density figure is your distance, your mass, or your frequency. I'll show you more about that in a second. It's a very simple equation. Oh wait, I already did show the equation. Yeah, so they fall off like 1 over distance. So if you're really nearby, you're screaming. It's okay. Actually, the very highest peaks up here, we think you should just be able to resolve anyways because they're the loudest signal by a country mile. Yeah. Okay, so this is one way of thinking about this. The other way that I've started to think about LISA sources is actually just like what could we observe? Not necessarily what theory says we could observe, but what is just possible with LISA. And to do that, you create figures like this one. So this is actually taken from legwork documentation that Tom wrote. Oh my God, I didn't say his name. Tom Wag wrote legwork with me. He's tip-top. Really genuinely lovely. So this is a different way of thinking about the LISA curve. You can see these high frequency wiggles. So the sensitivity curve is in here, but it's a little different. So what I'm showing you on the y-axis is the mass of the binaries. On the x-axis is the orbital frequency, and the colors are what we call a horizon distance. So that says if there is a binary radiating with this orbital frequency on the x-axis and this chirp mass, LISA will observe it to some distance. You can put useful things on the curve to kind of orient yourself. GW 170817 is pretty high up. We saw GW 170817, that's the binary neutron star merger, with ground-based detectors very easily because it's at higher frequencies, much higher signal. something that's very exciting about this is that the galactic center is actually a pretty low frequency. So LISA is going to see a lot of things outside of our galaxy. That's one thing to get pretty stoked about. There's another feature in here that's kind of wonky, and that's this. So this line actually shows you during a LISA observation time, at these frequencies and this mass, the binary will chirp out of the LISA band. Any system that's above this line, you should actually be able to observe in ground-based detectors if the physical size of the object fits into that orbit. Double white dwarfs, you're not going to see that. Neutron stars and black holes, you're probably going to see that. Unfortunately for the neutron stars and the black holes, the observation duration kind of isn't so helpful, but good. Okay, so finally, this is where masses go. So any system that you can think of, you can just decide whether or not it's a LISA source by putting it on this figure. And you can make some pretty strong statements. So first, LISA will provide a complete census of every single double white dwarf in the galaxy with an orbital frequency greater than 3 millihertz. For people who build surveys, this is like what they chase. Like you're like, oh man, a complete survey for the whole galaxy, literally the whole galaxy of double white dwarfs. We pick them all up. LISA will provide a complete census of double neutron stars out to 1.5 millihertz and binary black holes down to 0.5 millihertz. This is really helpful. And it doesn't have to be complete. I have to remind myself that like, as a gravitational wave person, I'm used to these complete surveys because that's like what comes for free. We know the detection bias of all the other sources too. So we know, oh, if it's not quite there, we still know how far out we can see it. And maybe it's not as far as the completeness of the whole galaxy. But this is one of the reasons that I love gravitational waves, is that their survey selection is basically trivial. And so this is one of the reasons that I think LISA is just 100% going to be a game changer for us. No matter what signal we observe, we know how representative it is of the population because you just write it down. It's very easy. There's one thing to keep in mind with this. The source parameters that LISA can measure very critically depend on measuring an orbital period evolution. So this is the gravitational wave strain that I showed you before. Oh wait, actually, preview. This is a function of gravitational wave frequency. We measure that with the wave, fine. But there's a degeneracy here between the chirp mass and the distance. That means that you could have a very low chirp mass system that's right in your front yard. That's what those really high white dwarf peaks were. You could also have a really massive system that's just far away. And those, you can't tell the difference. For the sources where we only measure this, we'll have to go to EM catalogs and kind of like rule out what's going on there. That's not a solved problem, but we do have 10 years. So we'll keep working. If you measure a gravitational wave frequency, we know that the sources are almost certainly mostly just evolving due to gravitational wave emission. You can solve for the chirp mass right there. I'll even circle it for you. This breaks that degeneracy. And so for systems that LISA observes a gravitational wave chirp from, you get a 3-dimensional position on those things as well as a mass. The mass is the chirp mass, though. Good. OK, so I spent literally the whole time just telling you about LISA. That's because I really just want to get it out there that like, if you're not thinking about LISA and you think about stars, like maybe start thinking about it. Like the time is now to really get in on the ground floor. For the rest of the talk, I'm going to talk about multiband and multimessenger sources. So for multiband sources, and for people who have, I guess, like been living under a rock, LIGO and Virgo and now Kagra have found merging double compact objects. The first one was found in 2015. The first binary black hole was found in 2015. The first binary neutron star was found in 2017. We now have 90 of them after just a few years. It's a pretty meteoric rise for gravitational wave astronomy. The LIGO collaboration is willing to say a few astrophysical statements. They're willing to say that black holes with greater than 45 solar mass exist, and they merge with other black holes. Spin measurements suggest the presence of lots of different formation channels. and that there are some parameters that are observed to be correlated. The reason that we can't say anything more is because for every binary black hole that exists, there's probably a new formation channel that could make it. The theorists went wild with these things. You can kind of like divide them into dynamical and isolated formation channels, but the idea here is, do the stars that make the binary black holes form together, evolve together, or are they dynamically put together in dense stellar environments? You can write down formation channel imprints that happen from each of these, and I'm just going to give you the most obvious imprints. The first one is in mass. So in isolated binaries, you don't get double mergers. You don't make a binary, have it merge, and then find a companion. That only happens in dynamics. This means that if you're using stars, stars have an upper mass limit to make binary or to make a black hole due to something called the pair instability supernova. You're not going to go above a limit. So if you measure a star, or a black hole that merged with a companion greater than 45 solar masses, the isolated binary people usually will say that's not ours. Sometimes they go a little wild and they say, maybe we could like push it up, but there is a limit there, and that is a pretty strong result. So there's spins. If you have a dynamical environment, the black holes don't know anything about the spins, and so when you're just randomly putting them together, you get random spins. Fine. Good. Then finally, the last one, which is my favorite, is that the eccentricity of the binaries that are created is not actually just an indicator, but it's proportional to the amount of dynamics. So if you're in very highly dynamical systems, like inside globular clusters, you have extremely eccentric binaries. If you form instead in the galactic field, you have very low eccentricities. And so if you can measure eccentricity with a gravitational wave, you can just write down where they formed. Unfortunately, for ground-based detectors, by the time you get here, there's no eccentricity left to measure. However, every gravitational wave source either forms in the LISA band or traverses through it. And so that means LISA measuring eccentricities for binary black holes does inform what's happening at ground-based detector land. So I'll give you some more quantitative results here. In particular, when GW 150914 was discovered, very quickly after, Alberto Susana wrote a really cool paper that showed LISA will, if there are binary black holes at high enough rates, LISA will measure them, chirping out of LISA, and can predict them to minute accuracy in ground-based detectors. That will be amazing, because if LISA measures a black hole here, and you know it's eccentric, you can watch it happen. Like, you can just watch the whole thing happen on human timescale. That's super cool. You can model the rates for what we think will happen. So based on LIGO rates, a small number to maybe a big number is a potential. From population synthesis, we have wider uncertainties because we're forward modeling the entire galaxy. So we have bigger uncertainties than a single measured LIGO rate. But this is a real strong potential. The cool thing that we showed back in 2016, and many people have continued to show, is that LISA can measure eccentricity of sources to really low levels. So LISA, this is a kind of wild figure. But what's going on here is I'm showing you the eccentricity versus the frequency. Sources form in the top left. They shrink and circularize and move down to the bottom right. This is the LISA band. This is where you can measure a chirp, where you can actually measure the gravitational wave evolution changing due to an eccentric orbit. And this is the measurement of eccentricity that you can do. So in a Monte Carlo study, every single system above eccentricity of 0.01 had a well-measured to 10% eccentricity measurement. 90% of them had a well-measured eccentricity here. So LISA will measure eccentricities of binary black holes to exquisite precision. The sources, so like a dynamically formed globular cluster source versus different galactic field sources, have different eccentricities. Unfortunately, they overlap in this plane, but for systems, which you measure the gravitational wave chirp, you also measure a chirp mass, and they just separate themselves out beautifully. So literally, Lisa will measure a system and be like, yep, that one was in a cluster. Like, cool, that's 1 for clusters, like 0 for binaries. And then it'll find another one, and like, we'll count it up and just literally read off whether binary black holes are mostly dynamically assembled or not. So that's cool. I posit this will not be useless by the time Lisa flies, because ground-based detectors are never going to measure eccentricities. So this is going to be the only way that we do this, I think. We can like get in a fight later about that if you have ground-based feelings, but.
Wait, so what's actually happening here? Why is it that the 1 CE and DC are different masses?
Oh, that's a fun question. This is because 0 CE, they just stably mass transfer. And so they don't lose envelopes. They keep the mass transfer in the system. Whereas if you go through a common envelope, you lose a lot of that envelope mass. So that's how you get the differences there. Also, globular clusters dynamically put heavier black holes together, usually. Yeah. So you up your chirp mass.
So does that depend on the fraction of the star that you think becomes the black hole?
Totally.
Yeah.
Yeah, this is, I think, this technique, I think, will be valid regardless, but there's a lot of movement in the sources here. Yeah, depending on uncertainties.
I'm surprised that they aren't more separated in eccentricity space. So,
yeah,
like, it looks like the separation is mostly just in mass space.
Yeah.
So, I don't know, can you talk a little bit more about that? Is it just, like, that they're both such broad distributions, or?
It actually goes back to this figure. Oh no, I have to do the builds. Ugh. Sorry. Good. In that 2016 paper, we only had the ejected sources. It's funny. It's a funny story. It's because Carl didn't know that you had to turn on GR in globular clusters. So then he did, and he was like, oh my God, we get lots of in-cluster mergers too. So if you make this 2016 figure again, which we haven't, which is kind of a drag, we should do that. You'll make a bunch that are
Yeah, so you're selecting only
even
the low
higher.
eccentricity
We're selecting
guys
on the low
because-
eccentricity guys from globular clusters.
Okay,
Yeah.
I understand.
Yeah. Good. Yeah.
I'd be a little bit pessimistic, though super excited. But what if we are on the sad side and only have 10 binary black holes?
We'll know which ones came from clusters and not.
Yeah.
Also, oh my, I don't have time to talk about it, but I have opinions. We can talk after. I have a
Yes.
fun idea that's going to take 40 minutes to say.
Okay.
But I've already used 50 minutes. Oh no. Okay. I'm going to zoom through neutron stars because it's kind of the same idea, except it relies on a different thing. So the rate of BNS mergers measured by ground-based detectors is much larger than the rate measured in the galaxy. We posit that that's because radio surveys are really bad at finding close binaries. They just literally put a factor on. They're like, radio surveys will not find anything here. That means that unless you're spinning really dang fast, if you're below a day, radio surveys can't find you as a double neutron star. And so we posited, well, there's probably a fast merging channel, but we don't know if that fast merging channel is because the neutron stars are dynamically assembled in globular clusters, or if they are assembled through isolated binary star evolution that just makes them very close when they form. This is a special formation channel that Thomas Taras has really championed. This is the channel that is basically required in population synthesis to get the LIGO rates right. The cool thing is that Lisa will tell you if the fast merging channel is eccentric or not. Because if there are double white dwarfs that are getting formed at 1 day orbital periods and they are not eccentric, Lisa's not going to measure very many of them with eccentric measurements. Instead, if they are eccentric, Lisa will just tell you. So Lisa will set that to rest, which is nice. Again, you have to wait some time, but that's fine. Oh my goodness, I had so much science to tell you. Okay, good. So for multi-band systems, Lisa will just unveil their formation environments, like for free. You don't even have to try that hard. So the theorists won't be able to write so many wild, crazy papers like we do with the LIGO papers.
That's not true. That's still right.
We'll do it. Okay, no, we'll find something else to do, for sure. We'll write a lot of papers. It just won't be about this anymore. All right, so as a reminder for white dwarfs, Lisa's primary source will be double white dwarfs. Every single one in the galaxy will be found with orbital periods less than 700 seconds. We can also predict that thousands of them, as I said, will have measured orbital periods and positions. We can also predict in our population synthesis which ones will be picked up in EM surveys. Unfortunately, the EM surveys really, whoa, goodbye. The EM surveys will only be picked up very nearby. That's because white dwarfs are dim. There's no getting around that. These will be really, really important, though, for a couple of reasons. So first, the thing that I forget is really, really important and valuable. Lisa will just tell us what the orbital period distribution is of white dwarfs. Knowing this tells you basically everything about common envelope. Common envelope changes this distribution as well as the slope. So you can just read off what common envelope is once you measure this. Easy peasy. You can also do really cool precision science. So if you are interested in the products of white dwarf mergers, if you observe the system with EM surveys, you'll get these masses because you can actually just observe the individual masses with a telescope. That's something that we do already. Lisa will tell us where to look for a lot of these. So this will make your TAC proposal a lot easier. If you say, we know that there's a system in this region that's a double white dwarf that has this chirp mass and this frequency, we're just going to drill and we're going to find it. That now becomes a possibility that we didn't have before without Lisa. And then once you observe them, you can just literally map type 1a progenitors. You can map how many white dwarfs at each frequency and at each individual mass exist. So that's cool. We'll also do really fun precision orbital evolution for accreting white dwarf systems, but that relies on us knowing the distance measurement. And that's because back before where I told you, oh, things just evolved due to gravitational waves. If you're an accreting white dwarf, the mass transfer actually drives your system evolution much more strongly. That means Lisa won't tell you anything about those systems unless you know how far away they are, because you need to calculate what f.gr would be for those systems, and then you can measure the astrophysics. But this type of precision measurement is exciting and important, but only possible with EM surveys. On top of that, Lisa parameter estimation improves by a factor of 2 for every system that we already know where it is. So EM surveys really unveil the power of precision science with Lisa. Okay, there's that. So Lisa will provide a census of broad properties for white dwarfs, but if you're going to do precision things, you really do need telescopes, and we love the telescope people for that. Okay, in the last very few minutes, I'm just going to pitch something. It's kind of like my baby, which is the idea that oftentimes when people say multi-messenger and multi-band, you're thinking, I got to see the neutron star emerge and then watch the fireworks that happen at the same time. You don't have to do that with binary stars. And in fact, if we're going to understand binary stars, we have to divorce ourselves from that idea, because you have to be able to transition between states. And I'll show you exactly what I mean here. So I showed you how binary evolution works on all these phases. You can distill it down to this, which is basically phases of evolution that you can observe. Lisa picks up here, ground-based detectors pick up here. Actually, I'll show you. Radio velocity surveys, X-rays, radio. you can observe binary stars all the way through all of these phases if you have theory to connect them. But the key is that you really need well-defined survey selection functions. Gravitational waves, we've got it nailed. Like, easy peasy. I've hopefully convinced you of that. Radial velocity surveys, we have examples of this. So the apogee survey is an impressively useful sample because we understand its selection function. Another really, really good example is the ELM survey. You can map that thing theoretically, easy peasy. ZTF, it's harder. ZTF has discovered the smallest white dwarf, the closest white dwarf, the tightest orbits of white dwarfs, but we don't know exactly what it means for everything else. And so work to map that selection function is extremely valuable. I don't have a ton of time to go through this, but I do want to very quickly highlight a study that I recently did with Sarah Thiel, who's a grad student at Princeton now, where we took this idea and ran with it. So we said we have very clear constraints on zero-age main sequence, star properties. We can apply a star formation model. We can simulate the population. We can connect that this whole process to what Lisa will see. You can find our paper. And because we used this lovely thing called Show Your Work, you can download our entire pipeline. And if you, in case you don't believe it for yourself, you can trust us. Our code's public. And what we did here is we just literally mapped this very clearly well-defined result that comes from Apogee and Kepler and other surveys that says we know this about initial stars. We can then map that forward into LISA. We know specifically, in this case, that the close binary fraction of sun-like stars is very strongly anti-correlated with metallicity. What this does is it actually just changes the orbital period distribution. So this figure on your left shows the frequency of companions as a function of orbital period. That word makes no sense to me. I've talked to Caitlin Crowder about it for like literally days. But what the punchline is if you integrate under this curve for a given metallicity, it gives you the binary fraction. That's what this means. It means that 15% of stars have a companion, and this is their orbital period distribution. That makes more sense to me than companion frequency. The punchline is that most binaries at low metallicity have closer companions, but we know from star formation that there are fewer of those stars formed. So now we can forward model all of this with cosmic. There's degeneracies that I don't have time to get into. But what we found is that you actually don't have to worry about the uncertainties in the ZAMs. What really matters for us is Roche overflow physics. So Sarah simulated standard model assumptions. She simulated very inefficient common envelope. She simulated very efficient common envelope. And she simulated no stars going into common envelope, basically on the first Roche overflow. And the number of sources that Lisa observes, we've shown it's not really going to change that much based on the binary fraction, but it will change by orders of magnitude in Roche overflow physics. So by nailing the first part down, we can actually do a lot of physics with Lisa on the outset. Okay, so I'm going to finish with takeaways. Sorry for like really going up against time. First thing, if you leave with anything, it's this. Lisa is absolutely a game changer, but it's not like a only Lisa kind of a deal. Lisa is a game changer, but it needs to connect to ground-based detectors, and it really needs to connect. Without it, it does awesome stuff, and it will specifically do really awesome stuff for double white dwarfs. But if you add in the other detectors, we can basically nail binary evolution. If you want to really constrain binary star interactions, you do need to do multi-messenger, multi-band, and most importantly, multi-phase stuff. So we should be prioritizing things that think about this if we want to understand binary evolution. And lastly, my plead to everyone who sits on TAC panels or funding or anything, we need to really prioritize and reward these surveys with those well-defined selection functions, because the 2020s and the 2030s is all about survey science, But if we're going to get what we get out of the surveys, we need to be able to map those selection functions back onto theory, or we just kind of get a lot of like cool nature papers, and then we're stuck with just, well, it's not a bad place to be, I guess, being stuck with nature papers. But if we want to make actual real change in understanding binary star interactions, we're going to have to understand those surveys. And that's all I have. Thanks.
Question? Andrea?
You mentioned the tacks are going to be happy because they're going to know where to look.
Yeah.
What is the error bar on the positions that LIGO produced?
So let's talk about it in terms of the frequencies.
And does that come out immediately so we can have a TOO and stop tracks of everything else?
You don't need a TOO. That's the thing that's beautiful. It's even better for the tacks. These things are going to be sitting here and really not changing their orbital period by any fraction at all. So for these here, 1 square degree and 10% distance measurements.
Oh, a square degree.
So it's
It's
tough, but we know that they're white dwarfs. So that helps you immensely because they're in a different color space. They're almost certainly much closer than you think any other star should be. But I think it's a lot easier to sell that than we want to look at every single white dwarf.
The point that it doesn't change is what you're saying.
Exactly.
I mean, I see all the tacks that want TOOs, and it's kind of tough.
Yeah. TOOs are like a thing of the past for LISA. You don't have to worry. They're not. Nothing is happening really, really fast. You can observe it in 1 year. You can observe it in 5 years. Yeah. Granted, maybe that's a problem for the TAC then, because then they're like, why this year? But we'll hit that when we come to it.
This way?
So I guess you didn't get a chance to talk about it, but I was curious to know how does the cosmological background affect identification of these binaries? Because what I'm wondering is if the supermassive black hole binaries are 100 times brighter than this, then how do you tell that apart? And whether there are any observational constraints for that population at all?
Yeah, so that's a fun question. I don't know the answer. I think, so I have an answer for you that's vibes, which is in conferences, no one is saying, hey guys, there's going to be a huge black hole background. People have been studying, doing predictions for these for long enough that I would guess that if there is a massive, supermassive black hole background that's dwarfing everything, we would have known about it by now. Or there's some new physics that we just don't understand. Where it really becomes a problem is that an SNR of 10,000 means that if you subtract it out of your data, you have this lovely time series that's coming in. If you subtract it to 1% efficiency, you wipe out 95% of the double white dwarfs. So the data subtraction is really where I think we need to push for those. And it's a little bit easier than you might think because these evolve on shorter time scales. So you can actually just, for the white dwarf binaries, if there's something that's coming in and it's just an hour of data, just cut the hour of data out and say, this is just that binary black hole, don't worry about it. So it's kind of like a separation of time scales, which helps us, and then better data analysis that we'll rely on, and then finally vibes. Because really, no one is talking about that yet. I also think LIGO measurements of rates suggest that these merging binary black holes, they will not form a background. We can calculate that as 100 max in LISA. So that's not a background. That'll be easy to pull out. Yeah.
All right, we've got to pack it up, but Katie's here for the rest of the day. We still have a slot at dinner if anyone wants to join. Thanks for a lovely talk.
Thanks. Thanks for questions. Just pull that out. I waved my arms too much. Thank you.